So we need to look at a basic thermodynamic law, which is that heat goes from hot to cold. So the first law of thermodynamics is the conservation of energy that we know already. The second law of thermodynamics, or one of the versions of it, is that heat goes from hot to cold. We know that hot things get colder. So can this possibly happen? We've got two bodies at 50 degrees and 20 degrees. The question is there a scenario where there's a spontaneous greater energy flow from B to A than from A to B? And the answer, of course, is no. The second law of thermodynamics asserts that thermal energy cannot spontaneously transfer from a region of low temperature to a region of high temperature. This underscores the fundamental principle that heat goes from hot to cold. Now, consider a cylinder as our system. When the air inside is heated, it expands. It gets hot and expands. And in expanding, it performs work on the surroundings. So now what? For the cycle to continue, the cylinder cannot expand indefinitely. Instead, it must contract. And to achieve this, we need to cool it down, extracting the heat, which causes it to contract again. This energy is lost to the surroundings and is degraded. To summarize, a heat engine can perform work, but some heat energy must be lost to the surroundings for the cycle to persist. That means it can never be 100% efficient. So let's recap the ideal gas cycle. During the BC expansion, the gas performs work on the surroundings, WBC, while during the dA contraction, the surroundings does work on the gas, which is work of dA. Comparing the areas under BC and under dA, we notice that BC's area is larger, indicating the need for additional energy input through heating and removing through cooling. This intricate process defines a heat engine where heat is converted into work. So, in order for us to expand and do more work than when it contracts, we have to put energy in. So the energy in, the thermal energy in, is bigger than the thermal energy out. The thermal energy goes in over the lines ABC and it comes out CDA. This is a heat engine. The heat does the work. If we turn to the reverse scenario, let's explore the cycle in an anticlockwise direction. During the AB expansion, but this area under AB is quite small. However, when we go do the CD contraction, the surrounding does work on the gas. And the area under that is much more significant. So this surplus energy in this case leads to what's called a heat pump scenario, where a small input, heat input, results in a larger heat output. So you notice that we have a small input on CB and BA and a large output on CD and DA. This energy, thermal energy out, is bigger than the thermal energy in, but you don't get it for nothing. You have to do extra work to do that. And that's what we call a heat pump. So heat can go from a cold area to a warm area, but you have to do work to make it happen. Now, in summary, for a heat engine, heat is input to perform work, but a portion of that heat must be ejected to maintain the cyclical behavior. So this is the system. The system is doing work and the heat is doing this, but to make it cyclical, we have to throw some energy out. The energy comes from a hot source and it goes out to a cold source. The only reason that energy flows is because we've got hot and cold. In this case, we have a heat pump. We do work to the system, we produce heat, but we need a smaller quantity of thermal energy needs to go in to make more thermal energy come out. But that difference is made up by the work that we do to make that happen. So here we have it. This is the work done. So the heat does the work, but some heat must be ejected in a cyclical process. For example, heating the air cylinder. On the other hand, you can get some in the system, some thermal energy is going in from the cold source, and you can produce more energy which is coming out, but you must put work in to make that happen. So this is a heat pump. So heat travels from cold to hot only if you do work to help it. It's like rolling a ball uphill. For example, in a refrigerator, you take the cold source, which is inside the fridge. You use a mechanism to, you do electrical work, so you have to plug it in, and then that hot energy is thrown out the back of the fridge. So it's impossible to build a cyclical heat engine without transferring energy, some heat, to a cold reservoir. This deficiency is reflected in the efficiency equation. Since there will always be some energy that is lost to the cold reservoir, you can never get 100% efficiency. There will always be some energy which is lost. The importance of this is if you consider a power station, you know that you have a boiler that transfers thermal energy to the system, which is where the turbine is. So that energy goes to the turbine and that does the work. However, for this to continue happening, you have to remove some of this energy and that gets lost to a cold reservoir. So that energy must be sent that way. So a power station, by its very nature of the second law of thermodynamics, must throw out some of its energy to a cold reservoir. So in other words, it heats up the surroundings. You can't just turn all that heat energy into work in a cyclical process. Let's take the conditions for a steam engine. You've got a hot reservoir and a cold reservoir. The hot reservoir is the boiler, and the coal is burning to fuel the boiler. So this energy goes into the engine and that causes it to go forward. However, for this to continue, we have to eject some of the thermal energy. So that goes to the cold reservoir. So on a cold day, Thomas is more efficient. Now, if Thomas goes to hell, where the thermal energy source remains at the same temperature as the cold reservoir, there will be no net flow of energy. The engine would not function, and so therefore there will be no work done. So in other words, if Thomas the tank engine finds himself in hell, he's going to stay there.